Okay, so we're back, and today we're going to be discussing sections 1.5 and 1.6 in the University Physics textbooks by Freedman and Young. And these sections talk about significant figures, uncertainty in measurements, and estimates, and orders of magnitude. So let's start off by discussing significant figures. And a significant figure, we're going to define it to be any meaningful digit, which, in all honesty, that's the textbook I received and read. But in my opinion, that's pretty much like verbatim significant figure. Significant is the same as meaningful. Figure is pretty much the same as digit. So I guess it's better to just show you what significant figures are by example. And we're going to have to follow two rules when we're counting significant figures. The first rule is that leading zeros never count as a significant figure. And the second rule is that trailing zeros, which are just zeros at the end of a number, they only count if there's a decimal place. And we'll discuss why later on. But let's take a look at these three numbers and let's calculate how many significant figures they had. So by any meaningful digit, we pretty much mean any non-zero number. So this first example is going to have three significant figures because you have 5, 3, and 7, three meaningful digits. This second number we have, remember, we don't count the first leading zeros. We have three significant numbers in a row. We have a fourth after the decimal place, and we do have a trailing zero. And since there is a decimal point, we do count it as a significant figure. So this has 5 significant figures. Let's go into example number 2. We have 3, and then we have this 1 over here. But what about this 0? It is neither a leading zero nor a trailing zero. Do we count it? And the answer is yes, we do. Middle zeros also count towards being significant. Now, I kind of want to underline the point, the difference between these two numbers, 537 and 537.00. And I want to state that it is extremely important for us to understand why, although they have the same value, they don't have the same amount of precision. Because let's take, for example, these two blocks. These are our blocks, and these are our scales. And let's say that this scale is only capable of weighing to the nearest whole number, but this scale is capable of weighing to the hundreds place. Now, when you go to weigh this block right here, it's going to tell you that this block weighs 537. That's all you know. It just weighs 537. You don't know if it weighs 537.1 or 537.000001. This scale is incapable of this level of accuracy. It would be incorrect for you to assume anything beyond this whole number. However, this scale gives you the reading of 537.00 exact. You know, without a doubt, that there is nothing in the tenths nor the hundredths place of this reading, because this scale is capable of reading to that level of accuracy. However, it would also be incorrect to assume that it weighs 537.001 kilograms or grams, whatever you want to measure in, because this scale is not capable of reading to the thousands place. So although they might look like they have the same number, they have the same value, you don't actually know beyond the level of accuracy you're able to measure at. And that is what significant figures are all about. Accuracy. Accuracy and uncertainty in measurement. So for example, if you remember our second rule here, trailing zeros only count if there's a decimal. Well, maybe now you have a bit of understanding as to why. The trailing zeros here count because they give us some depth into the amount of uncertainty in this answer. They tell us that without a doubt, these values are 0. It's not a 1. It's not 537.1. It's not 537.12. It is without a doubt 537.00 exact. And that is why those trailing zeros are significant. Now, let's move on to how accuracy might be displayed. So, you might, in your studies of physics, see accuracy displayed in two different ways. You can see it as 537 plus or minus 0.02 millimeters, or equivalently, you might see it as 537 parentheses 0.02 millimeters. These two are exactly the same way. I will say that method number one is more often used. And what these pretty much tell you is that your true value is going to be within the range of 537 plus or minus 0.02. So that means that it's within the range of 535, that's incorrect, 536.98 millimeters and 537.02 millimeters. So all we did was, to this side, we subtracted 0.02 from our base number here. From this side, we just added 0.02. That is why you see the plus or minus there. With that in mind, we can now move forward into the rules for adding and subtracting using significant figures, and for multiplying and dividing using significant figures. Because when you do multiple steps in a long problem, the uncertainties within each step compound into the final answer. So your rule when you add or subtract is to keep the same number of decimal places, as the number with the largest uncertainty. So keep the same number of decimal places as the number with the largest uncertainty. Now, when you multiply and divide, your rule is to keep the same number of significant figures as the number with the lowest amount of significant figures. So with those two rules in mind, let's just go over some examples. Let's say we have 537.12 plus 63.7 plus 638.001. What we're looking for is the number with the largest uncertainty. The number with the largest uncertainty is going to be our least precise answer, which is 63.7, because we only know the true value up to the 10th place. And I hope that makes sense. If it doesn't, always feel free to leave a comment. So we know that our result will only have decimal point up to the 10th place. So our unrounded answer is equal to 1238.821. And since we only want the 10th place, our actual answer to the correct number of significant figures, we have to round down to the 8, and that gives us 1238.8. Now, let's do an example with multiplication. And let's say we have 67.12 times 100.8 times 39. Now, this first number has 4 sig figs. The second number also has 4, but this last number has 2. So we know that our answer is going to have a total of 2 significant figures. And when we calculate this, we get a number that is really big. And now, a part of you might be thinking, how do we convert this number to only have 2 significant figures? And what you want to do is use scientific notation. Now, scientific notation requires the use of an exponent here, and I always have to count. So it's 1, 2, 3, 4, 5. Got it. Okay. Now, what I've pretty much done here is that I rounded this answer to simply be 26, 1, 2, 3, 4 point 0.000. These two numbers are the same, but with different levels of uncertainty. But that's basically what this is. Scientific notation pretty much tells you that 2.6 times 10 to the fifth, you're multiplying 2.6 times 10 times 10 times 10 times 10 times 10, all the way up to the number that you have in your exponent, which is why these two numbers are equivalent except for their level of accuracy. This would be correct for our number of significant figures. Lastly, I want to touch on something extremely valuable and important. You will see these terms in your laboratories, in physics, or in chemistry, and that is precision and accuracy. And now, when you see the word precision, I want you to think of consistency. And when you see the word accuracy, I want you to think of truth. Now, let's take an example to illustrate the difference between precision and accuracy. Let's say again that we're weighing 2 blocks, and we know that these blocks weigh 20 kilograms. A precise answer simply means that you are consistently getting readings that are close to each other. But that doesn't necessarily mean that your readings are accurate, because we can say that if a scale gives us reading of 25.12, 25.11, and 25.15 kilograms, this scale is precise because these three readings are all close to each other. However, these answers, as you can tell, are not accurate. They are not close to the true value. Accuracy, on the other hand, would mean trials like this: 20.10, 20.7 kilograms, and 19.99 kilograms. Measurements are accurate if they are close to the true value, or at least to the value that we expect to receive. And that is the difference between precision and accuracy. Now, there are moments in which you can be precise but not accurate, as you can see here. There are moments in which you can be accurate but not precise. There are moments in which you can be neither precise nor accurate. And there are moments in which you can be accurate and precise. Now, we touched on precision but not accuracy with this first example, and we touched on accuracy and precision with this second example, because as you can see, these numbers are all consistently close to one another. So that is both accuracy and precision. For these other two examples, we're going to take this bottom left one, neither precise nor accurate. That's rather easy to imagine, because that would simply mean readings of 100 kilograms, 500 kilograms, and then 76 kilograms, both of which are neither consistently close to each other nor close to the actual value of 20 kilograms. So they are neither accurate nor precise. What's more tricky is trying to find out how something can be accurate but not precise. Because you would think that if a scale gets us close to our actual value of 20 kilograms, that the trial answers must actually be close to 20 kilograms themselves, right? Does that make sense to you guys? But the interesting thing is to then come to the conclusion that in order for something to be accurate but not precise, we have to technically define a range after which something is not precise. Like at some point, you have to say, okay, if the answer is 5% beyond the actual value, then it is no longer considered precise. The interesting thing to know is that there is actually no set definition for when something is precise or is not. it varies by the industry you're in, by the experiment you're trying to do, by the laboratory you're in. It can vary. So that's something to keep in mind in these 4 scenarios. And now let's work on some example problems. Okay, so we have example 1.3, significant figures in multiplication. And this states that the rest energy E of an object, with rest mass m is given by Albert Einstein's famous equation E equals mc squared, where c is the speed of light in vacuum. Find E for an electron for which m equals 9.11 times 10 to the negative 31 kilograms. And it's also important to note that 1 joule is equal to 1 kilogram times meter squared per second squared. I quickly want to touch on something extremely interesting. Now, as you can see, we're talking about an equation that we actually haven't learned yet, and which actually has more to do with special relativity and modern physics than the level that we're currently studying at. And I want you to take note of that. And I want you, well, I guess you don't have to, but I would like for you to consider simply appreciating the fact that we can learn advanced subjects while applying them to our simple concepts here. Because now you get the advantage of becoming slowly familiar with the advanced subjects you'll be learning later, while barely touching them in your beginning journey. So with that in mind, let's solve this problem. So there's actually one other thing we need. So let me go grab that real quick. We need to know the speed of light in vacuum. So I'm going to write that down. Okay, so that's our speed of light in vacuum. And if you didn't know, you can simply look at Appendix F in your textbook. So what we pretty much just have to do is substitute our values into the equation and just round to the appropriate numbers of significant figures. So let's go ahead, write that down, and get that all sorted out. Okay, here we are. Now I'm going to plug these into my calculator, and I will be back with the result. Okay, so it looks like we receive this as our answer. And remember, always try your best to keep the digits intact. I know it can seem kind of tedious, but in order to be the most precise scientist we can be, it's important to have those digits. Now, it did state that our answer should be rounded to 3 significant figures, and so this is actually simply going to become 8.19 times 10 to the negative 14 kilograms times meters squared per second squared, which is the same as 1 joule. So you could just write this as 8.19 times 10 to the negative 14 joules. Now, just so you know, energy will always be written in terms of this unit, the joule. Energy and joules, they go together. Now let's do one more problem. Okay, so this is the problem that tests our understanding of section 1.5. And it states that the density of material is equal to its mass divided by its volume. So what is the density in kilograms per meters cubed of a rock with mass 1.8 kilograms and volume 6.0 times 10 to the negative 4 meters cubed? Okay, so we write density, and if you didn't know, density in physics is often used with the letter rho. This is rho in Greek, I believe. And as it states, density is mass divided by volume, and all we have to do is simply plug in our answers and then round to the correct amount of significant figures. So remember, since we are multiplying, the correct amount of significant figures is going to be the least amount of significant figures in our factors, which is 2. So I'm going to go ahead and calculate this, and I will return with the answer. Okay, so this is equal to 3,000. 3,000 is a density, which, if we wanted to, or correct number of significant figures, it is simply 3.0 times 10 to the third. Kilo, remember the units, because I almost forgot. Kilograms per meter cubed. So that's going to be it for section 1.5 of our textbook. And remember, we simply discussed uncertainty and significant figures. And now we're going to move on to section 1.6, which is all about estimates and orders of magnitude. Now, honestly, this is a really short section. All you really want to know is that sometimes you need to guess, and it is simply okay to guess, and the textbook encourages you not to look up measurements for problems in which you don't have the exact measurements to. Now, with that being said, let's go work on a couple of example problems in which I honestly decide to completely avoid the textbook's advice, and I will be looking up measurements. So I will return in a second. All right, so here we are at example 1.4, an order of magnitude estimate. And it goes like this. You are writing an adventure novel in which the hero escapes with $1 billion worth of gold in his suitcase. Is it feasible for someone to carry that much gold, and would it fit in a suitcase? Now, in problems like this, in which you're giving a problem but not a lot to work with, a lot of the times you either have to guess the measurements you use, or you do what I did and you just look up values. So I just went to Amazon and I looked up suitcase, and I clicked on the first one and got these 3 measurements for that suitcase. Now, since I've already worked out this problem before, I know that we also need the density of gold and the price of gold per gram. Now, typically, problems like these, where you're not given much information, we're all going to have like different ways of solving them. The way that I solved it is different than the way shown in the textbook. So just keep that in mind. And the first thing we're going to do is find the volume of the gold that would fit in the suitcase, which pretty much is just finding the volume of the suitcase. Then we're going to convert this volume to grams and then to pounds to see if a human would actually be able to carry that many pounds. After that, we convert from grams into money to compare the money that would fit in the suitcase to the $1 billion that he supposedly fits in a suitcase. Step number 4 is to evaluate. Now, with that game plan all said and explained, let's start with number 1, converting the volume. So for our dimensions, we have the following numbers. Actually, let me write it down differently. Length is equals to 21.5, width is equal to 14.1, height is equal to 9.3, and these are all in inches. Now, if you paid attention, you'll see that our density is in centimeters cubed. So what I'm going to do is convert from inches into centimeters so that all of our work is dimensionally consistent with one another. And if you don't remember, it's 1 inch is equal to 2.54 centimeters. So I'm just going to multiply each of these by 2.54. And that's going to give you the following 3 numbers. Okay, so these are our dimensions in centimeters. And as you can see, I've left them unrounded, not to the appropriate number of sig figs, which should be 2. And I'm going to keep doing that until I finish the actual calculation itself. So the volume is going to be simply the 3 numbers multiplied by one another. Okay, so this is what you should be getting for your volume if you're following along with me. Now, in order to convert this to the appropriate number of sig figs, I need to use scientific notations, and I always need to count to know how many exponents there are. So it's going to be 1, 2, 3, 4. 4 exponents. Got it. And remember, this is in centimeters cubed. I sometimes do forget to put the units where they should be going. But okay, our volume of the suitcase is 4.6 times 10 to the 4 centimeter cubed. Now, what we need to do with this is technically the volume of the gold that would fit in the suitcase. So now we convert this volume into grams and then into pounds. So in order to convert a volume into grams, that's basically converting centimeters cubed to a mass. So we're going to have to use the density formula, the density of gold, which is 19.32. grams per centimeter cubed. And remember, mass is equal to density times volume, which is, again, this is your unrounded answer. Now, it's going to be to two significant figures, so you should end up with something like this. 1, 2, 3, 4, 5. And this is in grams. Got it. So we got our weight of the gold in grams. Now, I don't know about you, but I don't typically lift things in grams. I'm more used to lifting things in pounds. So in order for me to be able to understand how much this weighs, it's easier for me to convert this into pounds. Now, I had to Google up this conversion ratio from grams to pounds, and basically what it is 1 gram is equivalent to 0.00220.462 pounds. And if you do that multiplication, you end up with the following number. Now, again, this should be rounded to two significant figures, which ends up being just 2,000 pounds. Now, 2,000 pounds is a lot. I think that's 2 tons. Is a ton 1,000 pounds? I'm not sure, honestly, but this is a lot. For example, I do strength training with dumbbells and weights. I can only bench press about like 200 pounds max. And so I would have to be able to bench press 10 times my current maximum in order to bench press this amount of gold. And that's a bench press. That's not even carrying the gold. And so what we can conclude is that no, carrying this much gold in a suitcase is not feasible. But the question didn't ask us if this much gold was possible to carry. It asked us if $1 billion worth of gold was possible to carry and if it would even fit in a suitcase. So now the question remains, how much money in gold do we have in here in this specific suitcase? So in order to find that out, we have to go back to our grams, to our mass of gold, and convert from grams to money. And we do that by taking a look at the price of gold per gram. Now, when you work this out, you get the following number. Again, should be rounded to two sig figs. 1, 2, 3, 4, 5, 6, 7, 8. If anyone has a shorter way of calculating the exponents, I don't know why. I always need to count. It doesn't come easy for me to see it, to just see it. Now, if you don't know, 1 billion is akin to saying 10 to the 9. So, a billion is 10 to the 9, and our amount of gold in money is 10 to the 8. So, what this means is that we have hundreds of millions of dollars in gold, which fits in our suitcase. But if we were to add any more money, for example, we would need to multiply our number, our 10 to the 8, by another 10 in order to get 10 to the 9. So we would need to have 10 times as much gold as we do now in order for it to be like the amount of gold we have in the example problem. So the answer is no. This is not feasible to carry, and it would not fit in a suitcase. But as we did see, at least we do know that hundreds of millions worth of gold could fit in a suitcase. It just wouldn't be carryable by a human. At least I don't think. And so that's example problem 1.4. Okay, so that is going to be it for sections 1.5 and 1.6 of the University Physics textbook. Now, this is officially the finale of what I like to call just the introduction to science sections. Starting in the next video, we're actually going to be talking about vectors, which are actually like actual physics. We're getting into the realm of physics now. We're going to be working with vectors for a very, 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 very long time. So tomorrow, or the next episode, we are officially getting started. I will see you there later.